Hello, and welcome to our company, NDT Technologies. We are wire rope inspection specialists, and we have 39 plus years experience developing and manufacturing magnetic wire rope test instrumentation. Based on our long and successful track record, and proud of our unique accomplishments, we can speak with authority about our very specialized field of expertise. We have made unprecedented progress, and our technology is now head and shoulders above that of our competitors. Our motto is, "Let's outrun the competition." We are ushering in a new era of magnetic wire rope testing, MRT, with completely unrivaled hardware and software for the precise and rational non-destructive examination, NDE, of wire ropes. Presentation Overview. Number 1. History and milestones, R&D and achievements. Number 2. Our new generation MRT systems for the inspection of high-value offshore ropes. Number 3. Our Rope Guardian Continuous Wire Rope Monitoring System, CRMS. Number 4. A rudimentary introduction to our technology by way of some simple analogies. Number 5. What sets us apart from our competitors? Performance comparison of our versus our competitors' MRT equipment. Examples and discussions. Here is NDT Technologies profile. We were established in 1980 in South Windsor, Connecticut. Our areas of technical expertise are control systems, motion control, power electronics, gas pipeline inspection, for stress corrosion cracking. From the beginning, since 1980, we have focused on magnetic non-destructive examination/evaluation, NDE, methods, especially on magnetic testing, MRT, of wire ropes, and the NDE of high-value offshore ropes. Our history, milestones, and achievements. A timeline of our research and development efforts and achievements is presented in the following table. State-of-the-art MRT equipment allows the quantitative evaluation of wire rope loss of metallic cross-sectional area, LMA, and of localized flaws such as broken wires, single and in clusters, inter-strand nicking, and corrosion pitting. During our 39-plus years of research and development efforts, we improved the inspection accuracy of our MRT instrumentation. Here we define increasing stages of accuracy, as going from mere defect detection to measurement, to accurate measurement, to defect identification and then, to continuous rope monitoring. For the following discussion, we use our, quote-unquote, accuracy meter in order to indicate our progress. Some 40 years ago, when we started up our company, we first developed a very basic LF signal. Remarkably, all our West European competitors never progressed beyond this rudimentary stage. To this day, they are still using exclusively this now obsolete, and unreliable signal. By 1985 we had developed our, LMA, signal for measuring a rope's loss of metallic cross-sectional area. This LMA signal is a considerable step up of inspection accuracy. By 1987, we had developed our echo cancellation algorithm. With this algorithm, we can now offer a quote-unquote, true LMA signal. This high-fidelity signal is completely noise-free with unmatched resolution and accuracy. Starting in 1998, we developed our proprietary wire rope roughness, WRR, algorithm, which allows a reliable quantitative estimate of the number of external and internal broken wires, single and in clusters, including inter-strand nicking, and the severity of corrosion pitting. This algorithm is still evolving. Presently, we are extending it for the MRT of rope end terminations, such as sockets, etc. In 2010 we started developing our Continuous Rope Monitoring System, CRMS. This system is completely non-contacting, with a significant air gap between the rope and the inside of the sensor head. This non-contacting feature is required to avoid potential damage to the sensor head, or the rope. The air gap also avoids problems that can be caused by a rope lubricants or contamination. This system was successfully installed on an abandoning and recovery, winch of a pipelay vessel. Over the past few years we developed our new generation MRT systems for the inspection of high-value offshore ropes with diameters up to 165 mm, lengths in excess of 2,000 meters, and costs in the seven-figure range. Magnetic Non-Destructive Examination, NDE, of the world's largest wire ropes. This includes our LMA 650 system for ropes with diameters up to 165 mm, our LMA 550 system for ropes with diameters up to 140 mm, our LMA 450 system for ropes with diameters up to 120 mm, and our LMA 300 system for ropes with diameters up to 83 mm. Our Rope Guardian brand Continuous Wire Rope Monitoring System, CRMS. Continuous wire rope monitoring systems must be non-contacting, to prevent damage to the rope and/or the sensor head, and to avoid sensor head contamination by lubricants and debris. A considerable air gap must exist between sensor head and rope, as shown. Next, an introduction to our technology. All MRT instruments use magnetic flux methods that are, basically, extensions of the magnetic flux leakage approach. Here is a simple explanation of these methods by analogy. Magnetic flux leakage methods versus the quote-unquote water flux leakage method. For the following discussion we will use analogies, such as, water hose versus wire rope, hole in water hose versus discontinuity, for example, a broken wire, in the rope, water versus magnetic flux, water pressure versus magnetic field strength, water leakage versus magnetic flux leakage, vacuum cleaner versus magnetic flux decompression sensor. Here is how it's done. To inspect your water hose for holes, fill it with water and apply pressure. Then, wherever there is a hole, water squirts out. Use an active sensor. For example, in our particular case, a vacuum cleaner to scan the length of the hose. A leak is detected where the vacuum cleaner sucks in water. Analogously, to inspect a wire rope for discontinuities, apply a strong magnetic field to induce an axial magnetic flux at the saturation level. Then, wherever there is a discontinuity, magnetic flux leaks into the surrounding airspace, and is detected by our active magnetic flux decompression sensor. Based on our proprietary magnetic flux compression decompression method, NDT Technologies uses active sensors, also called flux decompression sensors, for the detection of discontinuities in wire ropes. The analogy is using a vacuum cleaner as an active sensor for water hose inspection. All our competitors use passive sensors as will be explained in the following. Remarkably, even without water pressure in the hose, an active decompression sensor, like a vacuum cleaner, can still detect holes by creating a vacuum and sucking water from the hose. Similarly, an active magnetic decompression sensor creates a quote-unquote magnetic vacuum around the wire rope, that draws magnetic flux from the rope wherever there is a discontinuity. In contrast, passive sensors, represented here by a sponge, require high water pressure for the detection of leaks. Analogously, passive magnetic sensors for the MRT of wire ropes, require strong magnetic fields to drive them deep into magnetic saturation. This is required for the detection of discontinuities in ropes by passive sensors. Please note that all our competitors use passive sensors. Next, let's discuss loss of metallic cross-sectional area, LMA, measurement methods. Here is a performance comparison of our and our competitors' MRT equipment. Depending on the application, NDT Technologies uses various coil with integrator methods, as shown. These methods will now be described. Now consider a wire rope of any construction. Wire ropes always consist of wires and strands that are laid in helical shapes of various complexities into the rope. We use coils as sensors, which is shown here. During an MRT inspection, the axial rope movement through the sensor head produces an apparent rotation of the rope cross-section. However, this does not change the sensor rope cross-section geometry. This unchanging geometry avoids rope noise and allows completely noise-free signals. For the generation of their LMA signal, all our competitors use Hall sensors, because they are easy to use. A typical Hall sensor arrangement is shown here. Note that Hall sensors are placed in discrete positions around the rope. As previously discussed, the helical arrangement of wires and strands together with the axial rope movement through the sensor head produces an apparent rotation of the rope cross-section. Therefore, in contrast to coils, for discrete Hall sensors, this rotation changes the sensor rope cross-section geometry, and causes excessive rope noise. To illustrate the performance of our MRT equipment, we discuss the inspection of a winch rope. This is a locked coil rope that shows winding on drum damage and corrosion, including corrosion pitting. Please note the completely noise-free signals. We inspected a 32 mm diameter locked coil rope. This rope was used for about 10 years as a winch rope. A visual examination revealed corrosion, including corrosion pitting between the first and second layer as well as the second and third layer. Here are the results from the MRT of this rope. The charts were produced with our computer-aided rope evaluation software. The top chart is a trace of our LMA signal, followed by the LF signal, and our wire rope roughness, WRR, signal. The x-axis indicates distance along the rope under inspection in meters. Note that these signals are noise-free, completely without rope noise. The small ripples are caused by, and indicate corrosion pitting. Large deflections are caused by winding on drum damage and corrosion-assisted LMA, which could also be called second-stage corrosion pitting. To emphasize the effects of corrosion pitting on overall rope deterioration, the scan length for the WRR trace is chosen as 1 lay length in accordance with ISO 4309. A 2% calibration wire, that is attached to the rope, can be seen in all signals. Proper calibration is necessary for reliable rope analysis and evaluation. This is a requirement for making rational and timely retirement decisions. A scan length setting of 5 lay lengths for the WRR trace, in accordance with ISO 4309, emphasizes the contribution of winding on drum damage to total rope deterioration. A histogram analysis gives the experienced inspector an overview of the entire rope condition at a glance. It will highlight possible problem areas based on operator-specified thresholds. In the upper chart the user selected a 2% threshold for loss of metallic cross-sectional area. So any loss of cross-section greater than 2% is highlighted in the LMA trace, with easy reference to distance in meters along the rope. We can also see threshold settings for the LF and WRR signals. Now, let's discuss our competitors' LMA measurement and signal generation. As previously discussed, they use discrete Hall sensors, which is the root cause of their extremely noisy signals. Shown here is a chart that illustrates our competitors' various signals. From top to bottom, we have their overall LMA signal, their LF signal, 4 separate LMA signals from 4 different Hall sensors, and a rope speed signal. Note that this is a very elaborate and perplexing chart. Apparently they consider all this confusing detail necessary. This complexity makes chart interpretation extremely difficult, or impossible. Their chart reading appears to be based mostly on guessing, educated or blind. Here are more details. First, here is their combined LMA signal. Then, their LF signal. And their rope speed signal. Next, 4 Hall sensors are arranged around the circumference of the rope as follows. Sensor 1 produces Hall sensor signal 1, as shown. Similarly, sensor 2 produces partial LMA signal 2, sensor 3 produces partial LMA signal 3, and sensor 4 produces partial LMA signal 4, as shown. During an MRT inspection, the helical shape of wires and strands in the rope causes an apparent rotation of the rope cross-section as the rope moves through the sensor head. As discussed, this changes the sensor rope geometry, which, in turn, produces rope noise. This is illustrated here. Please follow the cursor along the various signals, as the rope moves through the sensor head and the rope cross-section changes its position with respect to the discrete Hall sensors. Next, a discussion of our competitors' test results. Here is a critical discussion of our competitors' chart. The discontinuity in their sensor 1 channel is, obviously, artificial. It appears that it was produced by cutting several wires, or, possibly, a whole strand, in the rope. Remarkably, this discontinuity is not indicated in any other signal, especially not in their overall LMA signal, and, surprisingly, not in their LF, or localized flaw, signal. This is shocking, because the LF signal is much touted to be especially useful for the detection of this type of discontinuity. Based on this and other observations, we consider the LF signal of little value or useless. Here is the chart together with its slightly enlarged and more detailed representation. First, note the green arrows that highlight the cut wire discontinuity in the sensor 1 channel in both charts. Then, the red and blue arrows indicate the location of the discontinuity in the overall LMA and LF channels, respectively. Remarkably, there are no indications of this discontinuity in both the overall LMA and LF channels. They are completely drowned out by the rope noise. Note that Hall sensors must be in very close vicinity of a discontinuity in order to detect it. For this reason, the cut wire discontinuity is only visible in sensor channel 1, as highlighted by the pulsing green arrow. All other sensor channels only contribute pure noise, as indicated. As the above discussion shows, our competitors have excessively noisy signals. Again, an analogy can further clarify this situation. Detecting a signal in noise is equivalent to detecting a flower in a wheat field. Here is a flower in a wheat field, and we can draw the following analogies: flower versus signal, wheat versus noise, and mowing down versus signal filtering. Question: how do you find a flower in a wheat field versus how do you detect a signal in noise? Answer: you can't find a small flower in tall wheat, and you can't detect a signal in excessive noise. It is also quite common among our competitors to quote-unquote embellish their signals by filtering. Again, drawing on our analogy, this is the equivalent of mowing down the wheat field. In other words, the analogy is, if you filter the signal, in order to, supposedly, get rid of the noise, important information gets lost together with the noise. Versus, if you mow down the wheat, the flower is gone together with the wheat. After the above discussion, there is a legitimate question: with all their overwhelming rope noise problems, what is the use of our competitors' MRT equipment? Big question mark. After the above discussion of signal-to-noise ratios, here are a very famous engineer's opinions on this subject, together with the perceptions of his pointy-haired boss. Now, let's talk about our competitors' localized flaw or LF signals. As mentioned, the LF signal is qualitative only, and, therefore, cannot, and should not, be used for making rational wire rope retirement decisions. Let's discuss this by way of example. We refer to the previous locked coil, Winch rope inspection. Here is the chart. As mentioned, the rope shows significant winding on drum damage. At this point, only the LF trace is shown. The LMA and the WRR traces are blanked out. Now, consider one particular position along the LF trace, indicated by the bouncing arrow. Note that this location is completely unremarkable, and yet, this is exactly the position of not insignificant winding on drum damage. The actual situation is revealed by considering the corresponding indications on the LMA and WRR signal traces. Similarly, additional winding on drum damage cannot be identified and characterized by examining the LF signal alone, which is indicated here. Explanation. Please note that the LF signal only indicates the slope, or first derivative, of rope LMA, and not LMA itself. This exaggerates abrupt changes of the LMA signal, that, in the present case, are caused by corrosion pitting, and not by winding on drum damage. More gradual changes, which are caused by winding on drum damage, are suppressed in the LF signal. To explain the features and idiosyncrasies of localized flaw signals, let's, again, revert to analogies. In the following, specific attributes of LF signals will be explained by using topographic concepts such as mountains, hills, slopes, etc. Note that the LF signal only indicates the slope, or first derivative, of a rope's LMA, and not LMA itself. This exaggerates abrupt changes of LMA, which, in case of the present winch MRT, are caused exclusively by corrosion pitting. More gradual changes, that are caused by winding on drum damage, are suppressed in the LF signal. Analogy. The height of a mountain cannot be determined with an instrument that can only measure its slope. In other words, steeper mountains are not necessarily higher, and vice versa. For this type of measurement, gradual slopes of the mountain are usually not detectable, while very steep slopes, for example, of crevices on the face of the mountain, are comparatively overemphasized. For example, consider Mount Fuji in Japan. With a height of 3,776 meters, this mountain is very tall indeed. However, its slope is so gradual that even beginners can hike to the top in about 5 to 10 hours. Therefore, in terms of our analogy, the height of this mountain, translated in terms of the LF signal, would not, by far, be indicated to its full magnitude. Conversely, mesas and buttes, found, for example, in the American Southwest, are not very high with very steep flanks. Therefore, in terms of our analogy, these geographical formations would be very prominently displayed in LF traces. They would be exaggerated way beyond their actual significance. Let's elaborate on our analogies, using mountains, hills, slopes, etc. to elucidate wire rope MRT concepts. This GIF explains the notions of zero, or horizontal, and positive and negative slopes. For further explanation, we draw the contour of the hill. Note the arrow that indicates the instantaneous height of the cars, as they move over the hill. Next, we indicate the slopes of the hill. Using the language of calculus, the slope is the first derivative of height. Here is the first derivative of slope, which is the second derivative of height. What does this discussion of topographic features have to do with magnetic rope testing? To answer this question, we first observe that the contour of the hill is an excellent map of its actual shape, as shown here. Now, reverting back to our analogies, the contour of the hill is equivalent to NDT Technologies' true LMA signal. As shown previously, this signal is an excellent map of rope cross-sectional area. It is quantitative, and allows the reliable assessment of rope deterioration, such as winding on drum damage, broken wires in clusters, inter-strand nicking and corrosion pitting. Referring to our analogies, shown here are the slopes of the hill, or the first derivative of its height. Analogously, this is equivalent to NDT Technologies' LF signal. Again, using our topographic analogy, here is the first derivative of the slope of the hill, or the second derivative of its elevation. Reverting to magnetic rope testing, this is equivalent to our competitor's LF signal. Now, to illustrate the futility of trying to determine the actual rope condition solely based on LF signals, let's simply hide the LMA signal. Then, it becomes obvious that rope deterioration such as winding on drum damage, clusters of broken wires, inter-strand nicking, or corrosion pitting, cannot be quantitatively characterized. Usually, These types of rope deterioration are not even detectable by using LF signals alone. These signals are difficult, or impossible to evaluate. Therefore, if only LF signals are available to the inspector, he is forced to resort to guessing, educated or blind. These signals are useless, or even dangerous because they can lead to entirely misguided rope retirement decisions. Note that these findings have been very convincingly confirmed by independent round-robin tests between NDT Technologies and its major competitors. As previously mentioned, we use the first derivative of our LMA signal as our LF signal. In contrast to our competitors, the amplitudes of our signal are completely and inherently independent of rope speed. Our competitors' LF signals have two major problems. They use the second derivative of LMA as their LF signal. This type of LF signal is only very remotely related to the actual rope condition. It is essentially undecipherable. Their LF signal amplitudes are proportional to rope speed and depend on awkward rope speed compensation schemes using variable gain control. Without a rope speed signal, amplitudes become random and useless. Shown above is an example of such an LF signal. This signal is random and defies rational interpretation. We and our competitors offer LF signals. They are popular because they are easily implemented. For example, by using saddle coils, an antiquated MRT device that has been around for some 80 years. Here are major problems with LF signals. LF signals are not quantitative. They cannot be used for estimating the number of broken wires, single and in clusters, interstrand nicking, and the severity of corrosion pitting. They do not allow a rational chart interpretation, with inspectors having to resort to guessing, educated or blind. LF signals are unreliable, misleading, and, therefore, outright dangerous. Do not use them for making rope retirement decisions. Another well-known behavior of LF signals is that their amplitudes first increase and then, paradoxically, decrease, as the number of broken wires monotonically increases from single broken wires to clusters of broken wires. Most of our European competitors, to this day, offer only an LF signal of the above-described questionable qualities. They were never able to even produce a pseudo-LMA signal, let alone a true LMA signal. More recently, an attempt has been made to use pattern recognition algorithms like wavelets or so-called wirelets for LF signal analysis. The problem is that, rope deterioration, like broken wires in clusters, interstrand nicking, or corrosion pitting, is completely random without any recognizable patterns. The only exception is the signature of discrete broken wires. Therefore, these attempts are useless and a pure exercise in futility. As mentioned above, the amplitudes of LF signals first increase and then, paradoxically, decrease, as the number of broken wires increases from single broken wires to clusters of broken wires. This is illustrated by this chart. It shows that the number of broken wires typically increases about exponentially over time. In contrast, the number of broken wires, indicated by LF signals first increases, and then, paradoxically decreases as the rope deteriorates further. This deceptive divergence is very dangerous, and/or wasteful, as the true rope condition cannot be assessed, especially when it actually approaches or even exceeds its retirement conditions. Besides the above-discussed performance of MRT instrumentation, the actual on-site use and handling of sensor heads by inspectors will now be reviewed. With respect to weight, there are two categories of sensor heads. Number 1, relatively light sensor heads, that can be handled, and mounted on the rope under inspection, by one or two inspectors without mechanical lifting devices. This includes our LMA 300 sensor heads for ropes with diameters up to 78 mm, and a weight of, say, less than 34 kg. This situation is further illustrated by the cartoon. Number 2, very heavy sensor heads, that can only be handled, and mounted on the rope under inspection, by using mechanical lifting devices. This includes our LMA 650 sensor heads for ropes with diameters up to 165 mm, and a weight of, say, less than 200 kg. Again, this situation is illustrated by the cartoon. The following videos document round-robin tests that evaluate the actual on-site use of our large LMA650 instrumentation against our competitors' comparable equipment. The first set of video clips illustrates NDT Technologies' calibration and inspection procedures.
The wires in. Pull it up. Out. Out. Just put it in, pull it up. Put it in? No, it's all set. Go. Stop. Go. Wieder. Again. Okay. Once again? Yeah. It's in. No. Pull it out. Go. And out. Okay. Up.
Okay,
Okay. Start.
go,
Down. Nee. Up.
up,
Attention. Attention. Stop.
Please note that, even for our very large sensor heads, we use a hinged clamshell design. This makes manual mounting on, and removal from the rope under inspection relatively easy. Of course, this must be assisted by mechanical lifting devices. The following video clip illustrates removal of the sensor head from the rope. As an aside, while no video clip is available, sensor head mounting on the rope is just as, relatively, easy.
Und. Wow. Runter? Ja. Achtung, geht runter. Weiter? Ja. Das schlägt zu. Okay. Lassen wir erstmal.
While our hinged clamshell design allows rather straightforward and safe mounting of, even very heavy, sensor heads, all our competitors use much more complicated procedures. Supposedly, to make transportation of heavy sensor heads easier, they split their magnetizer sections into several parts. Paradoxically, this approach only aggravates the heavy lift problem, by adding the difficult additional task of manually handling ultra-powerful rare earth magnets. As anybody familiar with these ultra-strong magnets can attest, this is an awkward and dangerous job. The following video clips illustrate a competitor's clumsy attempt to solve one problem by compounding it with additional complications. The following are video clips of our competitor's sensor head mounting, calibration and inspection procedures. Step number 1. Inserting the two halves of the sensor head into a frame.
Ja, das ist
so.
Step number 2, mounting the two halves of the sensor head, including frame, onto the rope.
Warum haben wir das jetzt wieder so? Wenn wir mal runterfahren müssen, die letzte Mal. Ja. Der liegt doch da.
Eigentlich schlecht.
Den machen wir.
Jetzt die 3.
Jetzt habt ihr da 3 reingemacht?
Ja.
Step number 3, using cranks for urging the two halves of the sensor head toward the rope.
Faster, Adesa.
Ja, Faster.
Faster.
Mr. Donau. Faster, faster. Das war herrlich, ne?
Wer? Wo?
Ja, am London Eye war.
Achso.
Jerry Corbeck.
Oh. Das war die Reise. Ich sag dann, lass uns doch noch eine Stunde länger machen, da haben wir alle 6 Seile, die wir prüfen sollen.
Nee, 6 Seile sollen wir in 3 Nächten oder so.
Ja, aber ich sag mal den Augenblick, weil ich sage, wir machen die noch.
Genau.
Falls nächsten Tag regnet. Nee, nächste Nacht kommst du nicht raus, nur die Schütte.
Aber jetzt also schwer. Mittwoch war auch. 15:45 Gramm Taxi. Okay.
War die Seite schwer?
Das brauchst du mal.
Ach, dann hast du die leichte
vor 13 Uhr passiert ist. Wir haben erst Lunch und hält dann die Stunde war. Keine Ahnung, links hat wirklich 14:45 habe ich meinen
Ich schätze mal.
Speicher ausgemacht, alles abgebaut und dann noch mit umziehen und hin und her und alles einpacken.
Step number 4, wire up the sensor head.
Hab ich geändert, nee. Warte mal. 2 hab ich hier. Ja, aber war das nicht, dass es falsch war?
Modul 2 ist auch in Modul 2, ist alles richtig. Dann müssen wir nochmal meine Kabel benutzen. Schon richtig.
Wann haben wir die Kabel gewechselt?
Verwechselt letzten Mal. Bei der ersten Messung. Dann haben sie dann nachträglich nochmal geändert. Da hat man Modul 2 an Modul 1.
Die Würfel. Ich dachte genau andersrum. Na gut. Und ihr alles selber macht.
Calibration and inspection.
Braucht da mal Hilfe?
Unten.
Ja, hältst du hier oben fest und ziehst das Rohr raus, dann halt in die Garage.
Ist der gelb markieren? Nee. Hat man das doch genug?
We hope you found this presentation interesting. Thank you for your attention.